Hello, students. Today's notes is about unbalanced forces. I already have it written out, so you could write this down, and I'll scroll this down later, but I'll tell you when you can pause if you still need to write it down. But I'll quickly explain each slide, so I'll explain it, and then I'll tell you that I'm pausing, and then you can pause, and you could listen while you write, or just listen first and then write later. All right, so today we're talking about unbalanced forces. When we're talking about unbalanced forces, we are talking about the forces that are now causing for movement. So if you take a look up here, we have this little point called inertia, and I'm going to highlight these, but you don't have to copy the highlight. So this word right here. Inertia is everything that we've learned just recently, and that is when objects are balanced. Now, keep in mind, we mentioned that when objects are balanced, there are a couple of ways that they're balanced. The first one is if they're not moving at all. It doesn't mean there's no force acting on them. So, for example, like anything that's on your desk that's not moving right now, that is an example of a balanced force. Whereas another example is if an object is moving at a constant speed. So if a car is moving and it's not going faster or slower, we do call that balanced as well. So what is an unbalanced force? Well, this is when you apply force to change whether an object is moving or not. And so there are four ways where you could see this unbalanced force, and it is when you either make something move, you could push something to make something go faster, or you could slow it down by pulling it or pushing it to slow it down, or ultimately you can do the same thing to make it stop. Whenever you see these going on, in other words, the speed is changing. So anytime the speed is changing, then you know that you're dealing with an unbalanced force. All right, so you could pause right here if you want to continue writing this down. Now moving on, so what is force? Well, it's when you use energy to change speed. And I'm actually gonna just highlight this one first, or I'll focus on this. So it is when you use energy. And when you're using energy, you're changing the speed, which we also call acceleration, or you're changing the mass of the object itself. All right, so those are the examples here. Now, it's important to clarify that anytime we say the word accelerate, and there's the opposite, which is decelerate, that means you're changing the speed. Accelerate means you're making it go faster. Decelerate means you're making it go slower. So whenever you see the word acceleration, that's what we're talking about. And the object is any physical object. So force can only be used on physical objects. In other words, things like ideas, things that are abstract, things that we cannot see, or other forms of energy. Those are all examples of non-objects, and those don't have a mass. So then we can't really apply force if we don't have the mass there. So the formula that we use to then explain this is F equals ma. Oh, let me fix that. There we go. So F equals ma right here. That is Newton's famous equation, and what it stands for is you have the force of an object, and that equals to mass and an acceleration. Now, this is a relationship. So in other words, what we're doing here is we're not actually saying that force has to be mass times acceleration, but we're saying that if you have an acceleration and you have a force, then you'll have a force. And if you have a mass, you can then make it accelerate or decelerate, and that's called force. So it's a relationship. You're using the force to then make an object accelerate. This formula will be very useful for us. So it's good that you note this and that you know what it all means. And we'll talk more about it tomorrow. But right now, so these are the units that we use. So whenever we are calculating these, we have to set or use these same units. So newtons is any kind of force. If you have any kind of force at all, we measure them in newtons. There's a number that we attach to it, and the bigger the newtons, the more force you have. So if let's say an ant steps on your foot, that is a very small amount of force, so the newtons will be very small. But if an elephant steps on your foot, then it will be a lot bigger. And Newton actually notes that this is based on the mass and the acceleration of an object. So for example, in the mass we'll measure in kgs, and the acceleration is using this unit right here, meters per second squared. It's almost like meters per second, but meter per second is the speed. So this is the change in speed, therefore it's meters per second, or to keep it simple, meters per second squared. You don't have to fully understand what this means right here, but it's at least you should know that that is the units that we're going to use for acceleration for this year. All right, so now if I scroll down a little bit more, you can pause here if you still want to continue this and finish writing this down. And then I'll scroll down. So unbalanced forces on an object. So let's look at an example, and let's say that I'm pushing this box to the right. So then we call the force used here the applied force. And then usually going against it, we have some kind of friction or resistance. And so anytime you see some kind of applied force, usually there will naturally be friction going against it. And that is just the amount of energy used to slow an object down. Now, friction is usually dependent on gravity. So it's really dependent on gravity. And if there is no gravity, then there's usually no friction. So gravity is the force pulling the object down. And as we established last time, normal force is the force that is pushing the object back up right there. So anytime you see the applied force, friction is always the opposite, and we have normal and gravity going opposites of each other, up and down. Now, you might deal with situations where there is an applied force where you're pushing an object down or you're pushing an object up, but we're not going to worry about it for this year. So all you need to know is that these applied forces, we're just going to focus on objects being pushed side by side. On Thursday, we'll talk a little bit about dropping objects, and in that case, we'll talk about mass and weight and all that too. But for today, we don't have to worry about it too much. All right, and that's pretty much it for the notes.